Hello, I'm Bill Lane, instructor at Bellcore Tech. And in this module, we're going to talk about the distribution part of the telephone network, sometimes referred to as the outside plant. But as we'll see, it's a lot more than just outside plant. What the distribution part of the network does is it ties the customer to the switching systems and to the transmission systems which are going to carry that message. So how does that work? Well, the customer has a telephone line in their facilities, whether that's in their house or in their business. That line is called inside wiring and it belongs to the customer. At some point, it comes out of the building and it attaches to the network at an interface device. Very often, that interface device was a set of carbon blocks that were mounted on the outside of the building, and these carbon blocks had two lugs on them, and the two wires of the telephone were connected to the two wires of the network. This provided the interconnection. As telecommunications devices have become more complex, we find that we require much more protection and much more sophistication in our interface. And now what you'll find is usually a fairly large metallic box with limited access, some sort of a control of a screw or a recessed a holding device that can be opened by the customer, and they will have access to part of this interface box which controls the inside wiring to their communications equipment. Another portion of the box, which has limited access to telephone company equipment, will provide access to the network. This allows a telephone company technician to be able to test the line from the customer facilities back to the central office, and allows the customer to check from the interface box back into their equipment. So it provides testing in both directions by the interested parties. Now, let's assume we're talking about a customer's house. Most of us are familiar with that, whether we have telephones in an office. In fact, we may not even work in an office. Let's look at a neighborhood. In a neighborhood, we've got a lot of nice little homes. And some of the older homes may be connected to the network through what we refer to as aerial cable, probably more commonly known as wires hanging on a telephone pole. This aerial cable connects through that interface box on the customer's premise to a small cable which goes up to the telephone pole. Now, because of this hanging from the upper to the lower, this is often referred to as the customer drop. Usually, you'll find 2 or 4 pairs of wires inside this little cable attached to the customer's property. Once it gets to the telephone pole, you'll find that it probably connects to an even larger cable in a fairly large plastic or rubber enclosed capsulated splicing area. That can be opened up and the customer's individual lines can be attached to the cable that carries other customer lines in that area. This larger cable then usually proceeds along through some other series of poles, and at some point it will probably go through an armored cable down under the ground and be carried back to the central office. Now, in some of the newer areas, telephone poles are not considered to be particularly aesthetic. So to make the areas look more wide open and more aesthetically pleasing, the telephone company buries the telephone equipment or puts it underground. So if we go back to this customer's house, they would have a little interface box on the side, but at this point it would go down and be buried under the ground and would probably go to a backyard or other access point where you might find a small metal box sticking up out of the ground, referred to as a pedestal. Opening up that box, we would see the connection points for that customer's drop to be attached to other customers' equipment and part of this larger cabling. This cabling then could be buried and travel along underground until it reaches larger facilities and gets to be larger and larger cable sizes. Now, this is where most of the terminology for the outside plant came in. Once we get into these large underground facilities, we require larger and larger splicing areas or big cabinets where all of these wires are connected together. One of the areas you might see is a large box several feet long, several feet high, and maybe a foot deep. double-doored, and it would swing open, and you would see a series of cables coming up the middle and going down the outside. This is where those individual cables from the local neighborhood customers are connected to the even larger cables, which go back to the central office. This is called a splicing box, or sometimes called an interface box. The larger cables now that go underground are more permanent because we don't attach them and detach them like we do at the customer's facilities. So rather than just bury them in the ground, we put them in more permanent structures. These large structures used to be called manholes, but because more and more of the work going on requires significant different pieces of equipment and more complex pieces of equipment, these have been changed through evolution and are now referred to as splicing chambers. And again, inside these concrete boxes, which is really what they are, buried in the ground, you will find the cables have places where they're opened up and they can be spliced together. For example, if a customer has a problem, maybe someone knocks down the telephone pole, or an animal chews through the cable on a pole, or someone's digging a hole to put in a deck and accidentally drills through their cable. This is where a technician can get in there and attach them to different cables to provide continuing service. This larger cable, as I said, is more permanent. It's not often gotten into, hopefully, is usually put into these concrete boxes, and they are in turn connected through hollow tubes. Originally, these tubes were made out of concrete, but they were very large and very heavy, and as we continue to expand, they've become hollow plastic or hard rubber tubes. We refer to these tubes, whether they're the concrete cement ones or whether they're the plastic ones, as conduit. Large tubes by which the telephone cables pass between these cement structures. Now, many of our customers are getting even more sophisticated. They're going well beyond just telephone equipment. And we're putting in data sets and computers and other electronic controlled devices. This requires different types of transmission or types of cable arrangements. Requires us to not put them just in concrete boxes in the ground. Because if you've ever driven around and see the top of one of these access holes, they're usually a round metal plate, and they have holes in them to allow them to vent the fumes out and let the air in. Unfortunately, this also allows water and other kinds of atmospheric conditions like snow and dirt and dust and even little critters to get into these boxes, making them somewhat undesirable. It also makes it very difficult for the electronic equipment that might be housed in these boxes. So new pieces of equipment, concrete boxes which are entirely sealed, they are heated, they are air conditioned, they have pumps in them to make sure the water stays out, they have alarm and monitoring to look for gases and other atmospheric problems. We refer to these as controlled environmental vaults, or CEVs. They do the same things that the splicing chambers do, but they do it under controlled conditions because very often they have, as I said, some very sophisticated electronic equipment in them. Now, these cables that run through these splicing chambers and these CEVs continue back, getting larger and larger as they approach the central office. Central office is usually a fairly large building somewhere in the center of town, which is strong commerce and business areas because that's where most of the demand is. The cables enter through the basement, so they come in underground out of this conduit, come up through some cable vaults, as they're referred to, or just large enclosed rooms, up into the point where they attach to the equipment in the central office, which we refer to as the main frame or the interface frame. So this is how this equipment is attached. You can go from the customer via telephone poles or aerial, or it can be buried in the ground, actually just plowed or trenched, a big hole dug, the cable laid in it, and the dirt covered back up. Or it could be an underground structure such as splicing chambers or CEVs, which are connected by conduit, and this is very often referred to as underground to distinguish it from that cable that's buried and laying right in the ground. Well, what kinds of cable are we talking about? What does this cable look like? And what does this cable do? Well, first of all, let's talk a little bit about what are the characteristics of this line that the customer is attached to. Well, first of all, what does this line do? Well, the line has to be able to provide dial tone. We've all picked up the telephone and heard the dial tone. That's an electronic signal coming from the office that says your phone is working and it's all right to start dialing. So then the phone has to handle the dialing. Primarily, there's two types of dialing. In the customer premises equipment module, we talk about a rotary dial, or that dial which operates manually. You turn it to an indicated point and you release it. It counts the number of digits that are operated depending upon the number you selected. The other one is called a dual tone multi-frequency, or a push button telephone, where we push one unique button and it generates a series of sounds which the central office receives and interprets as a legitimate number. So those are two different methods of dialing, and again, our line has to be able to communicate both of those types of signals. It also has to provide ringing. When we call someone, we hear ringing on the telephone to let us know that that other phone is working and they are not busy, and they hear ringing. And when someone calls us, we hear ringing. That's a different tone than we get with a dial tone or with the dialing. So again, the telephone line has to be able to communicate that information. How the telephone company starts. I'm sure several of us have picked up the telephone and dialed someone and actually heard them lift their receiver and talk before we heard their phone ring. That's because we had a collision of the calls in the network, and what we heard was a facsimile of their phone ringing. We didn't actually hear their phone ringing. Many of us may have even picked up the telephone to make a call and found someone already on the line. It's a little unnerving, but it can happen, and that depends upon the kind of electronic connection that we have. And that's what we refer to as a loop or a ground start. Well, let's look at what else our line can do for us. It provides a talking battery. Again, in the customer premises module, we said that we supply a DC battery signal which allows us to talk. When we talk into the mouthpiece of the telephone, we operate an electrical device which changes that battery voltage, and that's how our voice gets translated throughout the network. And lastly, our line has to provide the access for that number plan, that unique address code we have, and carry the voice traffic or the data traffic, which is the reason for the call in the first place. So the line has to handle all these different kinds of messages and signaling. What is the line made up of? What kinds of cabling do we have? Well, let's take a look. Looking at the types of cable we would see cable such as copper cable. Plain old pieces of copper wire which have been wrapped in protective devices, sometimes plastic, sometimes metal, sometimes combinations of plastic and metal. Cable that's going to be buried in the ground is going to be designed and built differently than cables that's going to be hanging from a telephone pole. Very often the cable that's hanging from the telephone pole sags and is subject to ice and snow and strong winds, so it's built with a supporting steel strand built right into its protective covering to give it that added strength. Of course, cable buried in the ground doesn't have that problem, so you wouldn't find it with that cabling. But you might find it with a protective jelly put inside of it to keep water and moisture out. Getting water inside a telephone cable gives us a lot of noise and a lot of problems. So by putting a moisture protectant device like a petroleum jelly or some other kind of device that fills up all the cracks in the cable, keeps the water from coming in. That would be much more appropriate if the cable laying in the ground than hanging on a pole. So we have different ways we can build our cable. Some of the cable actually has a pulp or a paper-derived product wrapped around each individual copper wire. We tend to find this more in the bigger cable coming out of the central office that's not going to be re-entered and re-spliced a lot. When it gets out to where it's more subject to damage out in the neighborhood, or where it'd be more easily entered and re-entered for splicing, we find that we tend to cover that not in paper or pulp, but in a plastic. A thin plastic coating is put around each individual wire to protect it from the other wires and from the elements. And as I said, very often these then are rewrapped into other plastics or metals to protect them. Sometimes we even put lead around them to protect them in really heavy traffic areas where they could be subject to a lot of damage. You might find that especially where you have rivers or oceans or lakes, where you might have people with boats and propellers on those motorboats will cut up a telephone cable very badly. Very often these cables are enclosed in lead for that added physical protection. But copper's not the only kind of cable that we use. More and more in the telephone network, you might hear the term fiber optic cable being used. What's fiber optic cable? Fiber optic cable is cable that has, instead of a copper wire, it has a glass rod. Now when we think of rod, we think of something very rigid and very inflexible. But in fact, fiber optic cable is very flexible. In fact, it can be bent and it can be twisted just like copper can. Unfortunately, if it's overbent or over twisted, because it has a glass product development in it, it can break. It can break like a piece of glass with very sharp edges, and it can also be punctured. So we have to be careful with it, but it is much more flexible than one would think a glass rod would be. It's also about the thickness of your hair. Now, how does that work? Well, it certainly doesn't work with electricity, because glass rods won't do very much with electricity. So with fiber optics, we have to use light pulses. That requires additional conversion. Let's take a moment and look at a little demonstration I've put together down in one of our laboratories to give you a little bit better idea visually about how this would look with a light shining down through a glass rod. Hi, welcome to the fiber optic lab. I thought this would be a good place to do a little demonstration on fiber optic transmission. And what we have here is a light source, a laser, and a glass rod, which we're going to use to simulate fiber optic cable. Now, we decided to choose the lab. We do have a variety of equipment down here and a variety of manufacturers that simulate all the different components and characteristics that you would find in a fiber optic network. And this is just one of several labs, so it just seemed like a good place to do the fiber optic demo. When you take into account that a laser source in the normal mode of transmission is about the size of, actually much smaller than your thumbnail, probably about the size of the end of a pencil, and it has to shine through glass cable that's probably the diameter of a human hair, you get some idea about the difficult nature of demonstrating that. So we're going to use these larger components to provide some good visual representation and maybe give you some visual idea about what this is all about. So I'm going to take the laser and turn it on, put the glasses on, and we'll shine it down through the tube, and or the glass rod actually, and you'll be able to see how the light travels down through this particular plastic rod. So I will turn it on and then open the aperture. And we'll use that whiteboard down there as the source to shine off of to give you an idea about the light. Now there you can see, hopefully, let me set this so it's stable, that nice concentric bright red light. That's transmission through the air. If we take this laser and we line it up through this plastic rod, because of the impurities in the rod, the light bouncing off them provides a little bit of visual representation of the light beam actually going down through there. Unfortunately, those same impurities create difficulties at the far end, and what you would see is the red light dispersed, spread out, misshapen, and just creating some transmission reception problems. But for our purposes, it provides a very nice medium to show. So we can see this red light, and you can see even with the size of the pieces of equipment I have to work with, alignment is very difficult both to acquire and to maintain. But doing the best I can, you'll see that red light traveling right down that plastic rod. Now what happens if it's not perfectly aligned? Maybe we can demonstrate what that would look like. Now I'm going to over magnify this movement, but in very small confines with very small components, it doesn't take very much to throw that alignment out. Hopefully you can see that light starting to hit the edges of that plastic and bounce back. And you can actually see that light turning and moving inside the plastic rod. And that rod's not polished, has no reflective surface, it's just bouncing off the edge and going back down. This not only disperses the light and destroys the medium, but it also changes the timing. And when you're talking about billions of bits of information a second, the very small delay that you would get from going through that rod could destroy the timing as well as the strength of that signal. If we look at what's happened to the light where it hit that board, you would see that the shape has changed, the intensity has changed, even the location, which is going to create tremendous problems at the receive end. So alignment is extremely critical, both for this reception of the signal and for the timing. Hopefully that will give you a little better idea of what a laser light might look like if you could see through that glass rod, and how critical the alignment is to the good transmission characteristics. Now I'd like to demonstrate a little something else to you. Let me turn this off. Very large, very hard, not very flexible. But in reality, the fiberglass cable that we utilize in communications is very flexible. It's wrapped in some sort of a protective coating, but it can be bent just like copper cable can. It can go around corners, it can go through tight spots. However, it's very important that we maintain that alignment. So let me simulate. I'll plug this in, turn the laser source on, and what you can see is that red light. And we'll put it through this tube. You notice when it hits my hand now, much more dispersed through this plastic. Also, the ends of these glass cables aren't polished very well, so we're not getting a very good signal. But in fact, that I don't have to have a straight, rigid device to transmit that light. And I can bend that cable in a variety of ways, and it does not affect my light source. So glass, even though it is glass, it's made out of the same types of components you might find real glass made out of, is very flexible, it's extremely strong, and the large size for handling is strictly for handling. It doesn't add anything to the capabilities, it just has to be large enough for us to be able to manipulate it as we pull it in alignment. So, while that certainly wasn't a very technical demonstration, I did want to provide you with a little opportunity to see visually about how this might work if we had, minuscule eyes and were able to get down to the micro level that you would have in the real world. So, we're actually able to send messages, not with an electrical signal over copper, but with pulses of light through this glass rod. It's amazing. Not only is it smaller and lighter, but because of its unique transmission properties, it can handle a lot more information than those two little copper wires coming to your house to attach to your telephone. But those two little wires that attach to your telephone carry your voice messages and to some extent your data messages from computers in a very good fashion. We could put in bigger copper coming to your home. We use larger copper tubes in the inner part of the telephone network where we're carrying large volumes of traffic. This is called coaxial cable. It's very thick center copper wires surrounded by a white plastic with a metal tubing around the outside. Quite similar to what you might see if you looked at the connection to a cable television to your home. But that's a lot more bandwidth or a lot more transmission capability than you need right now. So those two wires really do the job. But we could put in coax if you needed more, which is the big thick copper wire. Or the new technology is we could put in this fiber optic cable. Whether we're talking about copper cable or whether we're talking about fiber optic cable, we're talking about physical wires. problem with physical wires are you have to buy them, you have to install them, and you have to maintain them. And if they go across someone's property, you have to pay them for the right to use their property. This can become very, very costly. Fortunately, physical wires are not the only way we can transmit telecommunications information. If you think a minute about radio, radio reaches many people, and so does television, and they primarily transmit wireless. They transmit through the air. The telephone company does the same type of transmission. If you'll think a moment about cellular telephone or mobile telephone, we have a phone mounted in an automobile or carried in a briefcase or a purse or even in your pocket. The new little flip phones are small enough to fit conveniently into a pocket, but there's no wires on them. Well, how do they communicate? They operate like a small radio station. Unlike the radio that you have, you only receive information. You turn on the radio and you listen. Now, while you can talk back to it when you get upset or when you agree with it, they can't hear you. So you really only have a receive-only transmitter-less device in your pocket. But with a telephone, you want to be able to communicate both ways. Not only do you want to receive information, you want to transmit that. So you have this mini radio station. That makes it very difficult for the telephone, which is very small, compact size, to be able to transmit and receive both. In order to do that, you need an antenna. With a car phone, it's usually a piece of wire mounted on a window somewhere. With one of the portable phones, there's a small antenna sticking out of it. That's for your transmission and reception. But you have to communicate with another transmitter or receiver antenna. Those are usually on large towers along highways, attached to buildings, put on trees, a lot of other devices, anywhere up high where they can transmit and receive over a large area, much like a radio station. This mobile telephone network has advanced significantly. Initially, it was designed for a few dozen customers. That was all that was expected to be in the way of growth. So there was very few antennas and very few frequencies available for these telephone radios to work on. As the demand grew, and it grew much faster than anybody expected it to, we've gotten to a point now there is more demand for the service than there is capability. One way we can help that is to provide more and more circuits for these customers. But there's a limit. How can we possibly manage to address all these customers with so few antennas? Well, one of the things we're going to have to do is we're going to have to develop antennas that will be able to handle more and more customers, and in order to do that, they'll have to be in smaller and smaller areas. If we were to look at a layout of a cellular telephone, what we might see is a large antenna located somewhere along, especially in a populated area where there's a lot of demand. On the telephone installed in the cars is a smaller antenna, so that's going to limit the distance that we can go before we're out of range of that big antenna. Beside that, when we're attached to a car, we've certainly got a lot more battery than when we've got one of those little portable telephones. That means the distance that we're able to transmit and receive telephone calls is limited. So what we do is we set up an area. In this case, it's called a cell. It's sort of a multi-shaped, many-sided area within which this transmitter is able to pick up and send telephone messages. It then transmits back to another central office, only this one's called the Mobile Telephone Switching Office, and it provides the connection between this radio telephone link and the physical wires that go back into the regular part of the telephone network. Or, if the call you were making was going outside your area, the Mobile Telephone Switching Office would connect you with an inter-exchange carrier or long-distance telephone carrier. So, Advanced mobile telephone communications, or mobile telephone as we like to refer to it, consists of a series of many small sites, each one with a limited area. As cars or mobile telephones move from area to area, they are handed off through the switching office to the next antenna and so on around within the network. Now again, the limitation here with this type of arrangement is the low power so that they can reuse those frequencies from area to area. But that's not the only wireless technique that we have. Another approach that we use, as do many other industries beside the telephone business, is called microwave transmission. It is used to a large extent in the military, the railroads use it, trucking companies use it, and you've probably determined what it looks like without knowing it if you've driven along various highways and other approaches and seen these very large towers with what looks like a very large drum on one side and a cover on it. These are large antennas for a microwave transmission. As I said, the railroad uses them significantly, running right along the railroad tracks. That's how they communicate. Again, being wireless, it's not limited to having to buy all of that cable and to string it or bury it along a long way. So looking at microwave, we see very large towers with antennas at the top of them, and these antennas project a stream of data through the air in a straight line or line of sight. Now that can be a limitation. If those two towers are not perfectly aligned, you're going to miss that communication. Also, the curvature of the Earth. As you get 20 or 30 or 40 miles apart, the curvature of the Earth starts to play a role in it, so we keep these towers and antennas about 20 to 25 miles apart. So we can transmit tremendous amounts of data because microwave works like radio. We can project a lot of information in a straight line between two antennas miles and miles apart. But that's sometimes difficult to visualize. Let's take another trip down to the laboratory where I'll try and do another little demonstration for you and give you an idea how microwave works. Hi, I'm down here in one of the labs this afternoon. This one's the Digital Data Services labs. I want to talk about transmission. Now all this wonderful equipment designed around the room to operate has one major thing in common. It's all connected by wires. Some other equipment you might look at in a transmission lab is connected by fiber optic cable. There are some major advantages to having your transmission made over solid pieces of wire or fiberglass cable. First of all, it contains the signal, provides good characteristics, and over a long period of time has done a marvelous job for us. But there have been some inherent major advantages and disadvantages. On the disadvantage side, cost. Miles and miles of cable or fiber optics with repeaters and all other pieces of associated equipment get extremely expensive. In addition, it becomes subject to abuse, to damage, to vandalism, and to the elements. Right-of-way. That arrangement we make to run all of that physical equipment across someone else's property, whether it's an individual owner or a municipality, federal government. You need permission, very often costs associated with gaining that permission and that access. So how can we avoid that problem and still be able to transmit? Well, we can transmit through the air. I know that's not a new phenomenon. I'll bet you most of you are familiar with that. Broadcast television, broadcast AM and FM radio, in your car, at home, all broadcast through the air. Now, I'm not talking cable, I'm talking just standard broadcast. So what's the big deal? Well, with a broadcast network where we have paid advertisements, a lot of that is based on the size of the audience. So that broadcast is designed to reach as many people as possible. In our business, people are interested in confidentiality, privacy, proprietary information. We don't want it broadcast to everybody. So our transmitters are designed different. So are our receivers. These two little devices here that look like little square horns are going to function as our transmitter receivers. As you can tell, instead of being able to radiate in all directions, they're designed to be pointed in one direction and the radiation faces out from the end of the horn. Now, that works really well, but it does require very significant alignment. The two horns, or the transmitter and receiver, have to be very carefully aligned so that the signal doesn't go past. At this range, it's probably not a big problem. But what if it's 10, 20, 30, or even more miles apart? Alignment becomes very, very critical. Let's do a little demonstration. I have here a tape player, just an ordinary cassette player, and a tape I borrowed from one of the staff members. What I will do is I'll play the tape right through the speaker in the tape player. That has limitations. You have to be in the nearby area. It has to be cranked up loud enough. If you want to transmit long distance, it's not going to make it. We will then plug in our transmitter for our microwave unit on this side, and then we'll receive the signal over on this side. Got a couple ways of demonstrating that. We have a speaker, which will allow you to hear it. We have a meter, which will allow you to see the signal. And down in front here, we have an oscilloscope, which will provide a visual representation of the sound you're hearing. So you'll get to see it as well as hear it. And then we'll use some different applications to explain how that works and where it gets to be a problem. First, let's put on the music. Little leader there. Not too bad. But again, distance limitations. Let's see what happens when we plug it in to our network here. Now, I hope you can all hear that. You might even be questioning, what am I really hearing? Am I really hearing it come out of here? Is it really going through this area? Well, as you can see from the scope, the waveform is connected to this unit right here. The meter, which doesn't have to be moving very much because we don't have it on too loud, is connected also to the receive side, as is this speaker. I have here a piece of metal mounted on a stick. If I would place it between the transmitter and receiver, if in fact what you're really hearing is that signal, you should lose that signal. And we do. So the actual transmission is through the air between these two devices. Now, that means that while this is a major advantage because we don't have a lot of facilities, this kind of situation can be a problem. Anything of any size that gets between your transmitter and your receiver can interfere with your signal. In addition to that, if this is 20 or 30 miles, what about the weather in between? On a nice, clear, bright day or over the hot, sunny desert where there's very little to interfere, I can simulate that by this dry cloth. We don't have any signal problem. However, as this atmosphere picks up moisture and these clouds become wet, or as we add snow, or even a fog, an early morning or a late night fog, or perhaps a dust or dirt storm. Another rag, this one's just been wet. Notice the difference. Dry, wet. Even though water is a good conductor, in this case it's of no advantage to us because it absorbs the power. The greater the distance, the more power required. If it absorbs the power, it's not received. Let me stop this for a moment. In addition to that, the moisture beads tend to reflect the radiated signal and run it off into side directions. And therefore, it not only dissipates the energy, but it reflects the signal. So atmosphere can be a problem, and it's something we have no control over at this point. What about rain? If you'll allow me, I'll do a little example of rain, and hopefully I won't get too messy. Let me turn this back on. Here's my same wet rag. The rain can affect the signal just like a cloud or fog or some other high moisture barrier. As I said, a critical factor is the alignment. What if these should move slightly, a tremor, or enough movement in the earth to cause these to shift very slightly? I haven't lost my signal entirely, but I certainly lost a considerable portion of it. This is a great amount of movement, but it's a short distance. If I was 30 miles apart, it wouldn't take very much of an alignment to create a problem. There is one slight advantage to this, is even though these are line of sight, if I can use this metallic device as a reflector, I've lost a lot of power. I don't know that you can hear that necessarily. There we go. But now my signal is bouncing. It's straight line, but it's a controlled bounce. We can utilize that in our transmission as well. Rather than putting in a live receiver, we can use a bounce reflector, a passive reflector, and utilize that to our advantage where this line of sight technique doesn't lend itself to putting the transmitter and receiver. Oh, too loud. Okay, so we've got some interesting phenomenon here. We've got line of sight over a great distance. We've also got no intermediate facilities, so we've minimized our cost. We do, however, have the problem of security of the information because it is still radiating in space, and if you're anywhere near that, you can pick up that signal. In addition to that, it's subject to a lot of atmospheric problems. Now, to get the signal from the base transmitter, usually a little building down at the bottom of the tower, all the way up to the antenna, we don't rely upon free space propagation. Because I indicated it radiates in a lot of directions. Usually there's people, population around there. In addition to that, there's loss. One of the vehicles we use is called a waveguide. I have a couple pieces of waveguide here. Rectangular tubes in this case, highly polished inside, and the size is designed to match the transmitted frequency. So as the frequencies change, the waveguide is expected to change. This is designed to make a turn, and that curve is designed also to the frequency we're transmitting. Oh, this big beast would be another piece of waveguide. Round as opposed to rectangular, would operate at highly different frequencies, very heavy. You wouldn't want to do this very far. There still is loss in waveguide, even though the signal transmits up through the middle. As it bounces, as it travels, it loses some power. And all the power is down at the transmitter, not up at the antenna. Waveguide doesn't have to be hard, rigid. It can also have flex. This is a piece of flexible waveguide, corrugated inside, has a little more loss, as you might imagine, but it can allow us to make adjustments in the alignment between a transmitter and its antenna at the top of the tower. As I said, as the curvature of the earth interferes with it, we have to keep raising the antenna up, higher and higher on the tower. And when you start getting up too high, you start getting loss in the waveguide. So there are some transitions we have to concern ourselves with. There's some trade-offs we have to make. That's pretty much it for microwave transmission. I didn't want to overburden you with a lot of technical information, but I did want to give you a little demonstration of what microwave transmission is, some of its advantages and some of its disadvantages. Well, as you see, microwave has some advantages. It also has some of those disadvantages. For example, microwave and mobile radio are affected by weather, as is any wireless transmission. Rain or fog or snow can create substantial communication problems in a wireless mode. So where the trade-offs are economic, depending upon the weather conditions, we can have some service problems. Well, that pretty much concludes our talk of the distribution network, or that part of the network that connects the customer into the central office or into the switching equipment. We've talked about the customer being connected to the network through some sort of an interface contact, primarily an interface box which allows access for testing. At that point, the customer is normally connected through copper wires back to the network, either on an aerial, up on telephone poles, or buried under the ground. These then become cables that connect more and more customers, go through more and more connection points, or cross-connect boxes, or cross-connect terminals as they're referred to larger and larger cables which ultimately go back to the central office. The few exceptions we have to that are where we're dealing with mobile or cellular telephone, because they don't have any wires connecting them and they become transmitters and receivers in a radio fashion. And then we talked a little bit about how microwave works. It also has a wireless medium, but again is subject over long distances to weather conditions. So whether your wire is copper with an electrical signal being transmitted, or fiber optics with a light or an optical signal being transmitted, or in the air with waves of energy being transmitted through the air medium, our customer is connected deeper into the network. Now, in subsequent modules, we're going to talk about how those switches work, how that signal is transmitted over all the facilities, all the signaling that goes on to enable that to happen, and new and emerging technologies. And of course, we have other modules which deal with the customer premises equipment. Thank you for joining me.